Mir talks. Today we're enamored with the fact that we have Mir Mehedi Faruk giving us a talk on what are unaware of Mir Mehedi Faruk. He's PhD. He has a PhD in theoretical physics from McGill University, as now is a postdoctoral researcher at Shanghai Tech. Thank you everybody for coming, and I hope you enjoy the talk. I'm sure you will. Up to you, Larry. Thank you.
Thanks, Michelle, for the introduction. So can you guys hear me? Okay, so for last 20 years or 30 years, we had constant progress in ADS CFT. And through ADS CFT, about the quantum theory or the dual quantum theory of the black holes. Okay, so I think I should wait for a minute. It's okay? Yeah. Is it okay now? Yeah. Okay, cool. But so today's talk is about de Sitter black holes. And of course, we had much progress about the dual characteristic of ADS black holes, but ADS geometry is very different from the geometry that we live in. So that's why we want to have a quantum theory of the de Sitter black holes. Yeah. So we know that cosmological observations suggest that at very early and late time history of our universe is identified with exponential expansion, cosmological constant describing an exponentially expanding universe. So therefore, study of de Sitter space is crucial for our understanding of the real universe. Any observer in de Sitter space-time is surrounded by a cosmological horizon. But we know that whenever there is a horizon, there is an entropy. But we would like to understand what is the microstates associated with those entropies, right? And from ADS CFT, we had much progress in understanding these microstates associated with this entropy. So these are basically the 4 papers that the talk is going to be based upon. So in my PhD, in the beginning part, I mostly worked upon string theory and string cosmology stuffs. But the later part, I started working with some people in Amsterdam, and we basically focused upon understanding the quantum of the de Sitter. Although we don't know what is a dual quantum theory, there are like a couple of groups present around the world who are trying to do this kind of stuffs. So these are the 4 papers that we by next month or end of next, beginning of February, I hope. So I will start with something very basic, which is geodesics in Kirby spacetime. You know, so equation 1 is basically, you know, this is something that we know, everybody, that this is like the action for a point particle, right? And this kind of geodesics are very important to understand the causal structure of this spacetime. So let's say we start with a spherically symmetric metric of this kind, and basically then the geodesic equation of 1 becomes very easily becomes equation 3, and with the value of this epsilon, we can understand which are what. -1 becomes like space-like, 0 becomes null-like, and 1 is for time-like geodesics. Okay, so basically we have 3 kinds of geodesics more or less in physics, and this simple equation can give you the geodesic equation for the spherically symmetric metric. So with this spherically symmetric metric, you can actually understand different kind of geometry, like Schwarzschild black hole, de Sitter space-time, Schwarzschild anti-de Sitter space-time. They all can be expressed with this spherically symmetric metric line element. And I would say for newcomers and also the people who are in general interested in this subject of de Sitter quantum gravity, I highly suggest you to go through this paper. This is a very nice paper done back in the early 2000s, where they introduced this kind of geodesics to understand the causal structure of this space-time. So first, I will try to review the causal structure of anti-de Sitter space-time or anti-de Sitter black hole. So, is the mic working now? Okay, cool. So, how many of you are like familiar with the concept of Penrose diagram? Yeah, many people. Okay, very good. So, Penrose diagram is something very much used in physics, and in this paper, basically, these famous people, Witkowski, Hubini, Schenker, Kleban, they showed that for d greater than 3 spacetimes, the Penrose diagrams act in a very weird way when there is a cosmological constant present. Cool. So I will go slowly. So if you have any questions, please ask me. Yeah. Otherwise, it's just me talking. So you see that if you want to study causal structure, the fastest way you can send signals are what? Are basically photons, right? Or null light geodesics, in other words. That's the fastest way you can communicate. So that's why to understand the causal structure of the space-time, we send null geodesics or null rays from the observer to somewhere, and then we can measure how far are they, and where is the singularity, where is the horizon. We can all understand it. So picking like epsilon goes to 0 in this equation, we go to this simple equation, which is like the equation for null geodesics. Okay. And you see that this plus and minus sign, there are two signs. This plus and minus signs correspond to, one is outgoing null geodesics and one is ingoing null geodesics, right? Cool. So you see that equation 4, the r dot respect to the affine parameter, but of course they cancel and they become some simple equation like this. Just this part is very simple actually. So once you take the outgoing null geodesics, let's say we want to construct outgoing null geodesics, okay? And more or less, we all know what is a Schwarzschild black hole, right? That in the Schwarzschild black hole at r equals to infinity, there is an observer, and from where you can send null rays, okay? You can always send null rays, and at some point it crosses the horizon and goes towards the singularity, okay? So more or less, I assume that many people knows this. And now, just for clarity, we take equation 4 and integrate on both sides, right? When you integrate upon both sides, you see that you start from r naught, where the observer is initially, and r is the end point, right? R is the end point in your space-time. So we are taking just a space-time, and we are putting an observer somewhere. Let's say the observer is at fixed radius r naught, and from there I will start shooting null geodesics, and I will try to understand the structure of the geometry of the metric. So, is there any question with equation 5? It's understood. Yeah, it's a very simple one. So you integrate both sides, and this tau is the time, initial time for the observer, okay? And R naught is where the observer is fixed. Now, So this is like a typical solution for Schwarzschild ADS black hole. Yeah. So when it's like basically when you want to just study Schwarzschild black hole, right? You are probably many of you are familiar just with the Schwarzschild black hole. In the Schwarzschild black hole, this term is not present, right? So this is basically L goes to infinity, gives you the flat spacetime limit of this equation 6. Yeah. So this is like a 5-dimensional Schwarzschild ADS metric. And if you guys are familiar with ADS spacetime has a boundary, right? It has a boundary. And if you are familiar with the ADS black hole Penrose diagram, let me try to draw it here first. So basically, these guys are your horizon, right? This is the future horizon. And let me redraw it. This is the rubber, I think. Yes. Sorry. Yeah. Probably. Yeah. Sorry, where? L. Oh, L is the length of the radius. It's the length of the radius radius. So L goes to 0. Infinity means that it's a very big radius space-time, and basically it's a flat space. Anyway, for finite L, that then you have then you have like boundary at R equals to infinity at radius system, right? So this is the picture I think you will see in many of the birds. This is the diagram drawn for ADS black hole, and people have your left patch, your right safety, basically the right, like on the left patch of the anyway. So but I will now show that this is not actually the Penrose diagram of the ADS black holes. Actually, this is like the Penrose diagram for only for d equals to three dimensions, where like there is no dynamic degrees of freedom for gravity. Okay, cool. Let's go. So we know this equation, right? So in order to solve this for ADS, in order to solve this equation for ADS, what we have to do, we pick R naught, RO goes to infinity. That means it's starting from here somewhere, right? From the boundary. This R equals to infinity. And this we set as R goes to 0. That means starting from the infinity and traveling towards the singularity, right? So that's kind of null geodesic we want to study. That we start from the boundary and we cross the horizon and then travel towards singularity. Now, if you actually try to solve this equation, is that basically you will see that there is a real part associated with the integral and an imaginary part. So I guess many of you are interested with ADS CFT, and in this kind of language in ADS CFT, basically, you have this is your r greater than horizon radius. Sorry, where is that over? Sorry, this one. Yeah, r goes to rb. rb is equals to horizon. And then basically you have r less than rb region, and this region is also again r greater than rb region, right? And you have the singularity in the middle, basically. Yes. And here t is imaginary part of t is 0, basically, in this case. And when you will be crossing the horizon, the imaginary part of the t will always get some minus I beta by 4, where beta is the horizon radius. Okay. So this is basically, this is what happens when you actually cross the horizon. You get always a minus sign, a minus imaginary part whenever you cross the horizon. So if you are curious, you can try with this integral. This is a very easy integral. And you can see that for this kind of geometry of equation 6, when you put this in equation 5, you will always get a constant imaginary part given by the temperature of the horizon. But the funny thing is that there is a real part associated with this integral. Okay. So what this real part actually means? So the real part actually means that if you want to reach in the middle of the singularity, okay, that means you want this guy to become 0. You want this guy to become 0. In order to this guy to become 0, the tau must be real part of tau must be minus pi by 4. That means you have to start not from the middle, but a bit behind, like this. So only in this way you will actually reach the center of the singularity. Otherwise, if you start from here, you will not reach the center of the singularity, meaning that this will not become 0. So if this tau equals to 0, this guy will not become 0 actually. So this is what means that in order to reach the center of the singularity for ADS black holes, you have to start from a bit below from the boundary. And that's why the Penrose diagram is this weird shaped Penrose diagram. And for arbitrary d dimension, this tau is given by this. That means how much you have to go down. And you see when d equals to 3, this is 10 pi by 2, which is 0. So that's why only in d equals to 3, the Penrose diagram is actually this nicely square-shaped Penrose diagram.
Not really familiar with this, but
yeah,
the center of the or the middle part of the singularity.
Good question. So we are not concerned about that because it's actually all conformal diagrams, but the bending down actually means a lot, means many things. Why? Because let's say I take a point, this one and this one. If the Penrose diagram, if the singularity is like drawn straight, then they will definitely meet with each other before hitting the singularity, right? But for these cases, for example, I start from here or here, they will not reach the singularity. They will not meet with each other. They will hit the singularity first. So if the Penrose diagram is bent in this way, that means more and more points are actually less causally connected with each other. And this has actually very interesting consequences when you actually want to construct the safety duals. Actually, many people are still working on it very much actively in past couple of months, last 6 months, especially. I'm pretty sure you know this guy, Hong Liu. I write his name. So if you go to his Inspire profile, you'll see that he's also working a lot on this kind of topics. Description for this? No, because that's the point. I mean, this is not a when you want to construct the safety duals, you can actually connect this the safeties by bouncing of this this null geodesic in the singularity. So this will not become, of course, just simple GR at some point. Yeah. Sorry. Yeah. Just give me a second. Sorry, can you repeat your question again? Like to begin from the above or from the center X line. Okay, let's say like you mean this. Yes, they will not reach they will not meet with each other. No. But they can meet if they. Yeah, if these guys will meet. And in this, that's a very good question. Thanks, Walid. So I'm very bad in using these things. Okay, yeah. In this case, these guys will meet with each other. That means if you send null rays like this, they will meet with each other. But in this case, only these guys will meet with each other. And basically, yes, that's the question. That's the question. Is it like a specialty? So these are forbidden region, basically. Right? They will not meet with each other. And this is the extra part where it's forbidden. Right? Before it was until t goes to 0. Now you see it's quite below. So it has obvious consequence when you want to study ADS CFT. But of course, me as a physicist, I'm always curious about de Sitter space-time, and I wanted to see that if there is any analog of this kind of phenomena in de Sitter geometry. Let's go. So, as Walid pointed out, that when the Penrose diagram is bent in this way, right? The many of the regions are now not causally connected like before, if you compare to the square Penrose diagrams. Yeah, cool. So first, oh yeah, this is another paper I think quite interesting. They also have studied ADS CFT for this kind of actually bent kind of Penrose diagrams. Yeah. So we will not talk about it today. So let's talk about de Sitter. Yeah. So de Sitter geometry and ADS and BDZ geometry is actually quite similar. Let me draw it. So this is R goes to RB, and this is R equals to infinity, and this is R equals to 0, right? So this is ADS 3 or BTZ geometry. Okay. So this is the de Sitter metric that we're going to take. And like I said, this kind of spherically symmetric linear metrics are quite interesting because now you can take f of r like this, and then we will actually now study de Sitter geometry. And in case of de Sitter, what happens is that de Sitter Penrose diagram actually is quite similar to this. So de Sitter doesn't have like a singularity. Okay, de Sitter actually is similar, quite similar. Actually, you'll see that this is actually R goes to infinity, which is, sorry. So this is R equals to 0. Don't think they are like the in a singularity of the space-time, but these are basically what we call poles. These are called poles. And this is Scri plus, and this is Scri minus, we call. Scri plus is basically R goes to infinity, and this is also, Scri minus is also R goes to infinity. But in the late time. So this is, one is like future past and the, sorry, future infinity, and one is the past infinity. So we see that de Sitter black hole, sorry, just empty de Sitter geometry is actually a square Penrose diagram. Why? Because you see that when I actually fix now this for de Sitter, what we want to do, like so this one was for ADS black hole case, and this one I draw for de Sitter. For de Sitter, you start from your you set your R naught to 0 actually. This in this case. This is actually 0, and you go towards R goes to infinity. That means you are again starting from here, from R equals to 0, and you are going towards R goes to infinity. Right? So if you try to do this kind of integration again, that means what you have to do again, that you are integrating upon dr f of r, and instead of now you are going from 0 to R goes to infinity. So you can just do this integration first for arbitrary r, and that becomes like something like equation 10. And now if you take r goes to infinity, you will see that that it will become basically I pi L by 2. So yeah. No, because you want to reach the Scri plus, R goes to infinity. We want to we want to study the causal structure of the Penrose diagram, because the end of the de Sitter. So this is yeah, just this. This would be just static patch if you have integrated from R. So this is R equals to RC basically. So if you have integrated only up to R equals to RC, you won't access the whole universe. So that's the point, that every observer in the exciting universe can just are surrounded by some horizon. Or there is the end of the space-time is actually here at wait. Because at some point so this is the end of this is space-time Scri plus. So you want to start from here and end up in here. So that's how the whole space-time is accounted. And once you do that, what is quite different from the ADS black hole case is that you see that there is no real part associated with this integral. The real part is actually 0 in this integral. While in this integral, we saw the real part. This had a real part actually. So what it means that basically, if you want to make TDS equals to 0, so this is the end point. That means you want to reach the center of the geometry of the Scri plus or the future infinity. You have to start from tau equals to 0. And that's why just empty de Sitter is a perfect square, unlike ADS 3 black holes, ADS d greater than 3 black holes. So then my question was naturally like, what happens in de Sitter black holes? Because this Penrose diagram actually holds for arbitrary dimension, any dimension in de Sitter space-time. Basically, this is your R equals to RC, right? This is the horizon. And we saw that we just saw from this equation that if you shoot a null ray from R equals to 0 at the middle, the null rays meet simultaneously at the future infinity, right? Cool. So now that's why the de Sitter Penrose diagram, like I told you before, is like a perfect square. Yeah. That means actually something interesting again, that any points like these ones, yeah, they can be causally connected. They will get causally connected with each other before they hit the future infinity, right? So we'll now see a very interesting case, which is quite astonishing, or like quite surprising than before. Like in ADS black hole case, you remember it was like this, right? So now we'll see that in the de Sitter black hole case, because of the positive cosmological constant is very different than negative cosmological constant, we'll see a very different effect of the future infinity in de Sitter black hole. Let's go. So we start with something simple, that this is Schwarzschild de Sitter black hole, okay? And basically this guy is 0. That means f of r is 0 for RB and RC, two positive roots, two positive real roots. It has two positive real roots. Unlike the ADS case, unlike the ADS case where they have only one possible real roots. It has two possible real roots, and one is the black hole horizon and one is the cosmological horizon. So de Sitter has already a horizon here, although it doesn't have a singularity. It already has a horizon, meaning that if you make r equals to L, f of r is 0. So RC is basically L here, right? That means the root of this f of r is basically r equals to L. So basically this is the r equals to L. So now what I want to say that in this kind of geometry, it's quite complicated because it has two roots. That means it has two horizons. But de Sitter black holes actually has at least two horizons. One is black hole horizon and the other one is cosmological horizon. So conceptually, this kind of geometry is quite complicated. That's why Hawking started studying them back in the 1980s to understand the ultimate evolution of the black holes in accelerating spacetime. So, sure. Okay. Yeah, cool. And also, just a conceptual thing before I move on. Studying de Sitter black holes is also one of the hot topic and kind of going right now, because you know that in Schwarzschild black holes there is only one horizon. That means there is only one temperature, and we know more or less how to thermally equilibrium those. We know what are the thermal equilibrium states associated with those kind of geometries. But these kind of geometries are inherently non-equilibrium because RB and RC are not usually are equal to each other, and that's why you have two temperatures. And understanding the quantum theory of this kind of geometry is very difficult because you have two temperatures, and we don't know. And I think it's a still open question. People around the world, people in general, don't know how to write the quantum states for this kind of inherently non-equilibrium geometry. And just another quick anecdote is that unlike Schwarzschild, just empty Schwarzschild, just like Schwarzschild black hole, where again this guy is zero, right? Only this guy is present for Schwarzschild metric, right? So for Schwarzschild metric, just in flat space time, there is no bound on M, right? M can be arbitrarily big for Schwarzschild black hole. That means a black hole can be arbitrarily massive. It has no mathematical bound on it. But whenever you actually define like a black hole in de Sitter space-time, like this, like equation 12 in its full glory, then there is a upper mass bound of the mass for the black hole, and it's called the Naria mass. Okay. So it has an upper bound on the size of the black hole. That the black hole cannot be actually bigger than the universe itself. So in general, RC is greater than RB, right? That means the size of the universe is much bigger than the size of the black hole. But you can actually keep turning on RB, and the maximum value RB can reach is actually this, right? It cannot go bigger than this, and this limit is actually called the Naria limit. So it's not written here, but I can. These geometries are actually first studied by Hawking and Busso. I forgot the original paper references. It's not added here. I will let you know afterwards. But this Naria geometry is the maximum mass the Schwarzschild black hole can actually attain. Okay. So again, we start with we want to study the causal structure of the Schwarzschild de Sitter black hole. Okay, and before I draw the actual picture, I just want to give you like a like the version that was kind of known in the community. The Penrose diagram of the Schwarzschild de Sitter black hole was kind of known like this. So people thought before our paper got published, this was the common knowledge of the Penrose diagram for Schwarzschild de Sitter black holes, and the blue ones. Sorry, this one is R equals to RC. That means this is the cosmological horizon, right? And the blue one, this one is the black hole horizon. So you can start from the middle and go towards the singularity, or you can go towards the cosmological horizon. Okay, and now we will try to try to see the cases and actually solve the null geodesics and try to see if this Penrose diagram is correct or not. Okay, and for that, let's say we start with the 5-dimensional Schwarzschild de Sitter black holes. Okay, in that cases, what happens is that the RB and RC can be written in a very nice way. That's why we want to study that. But once again, I want you to remember this simple geodesic equation that I showed at the very beginning, right? That this is a gem for us, right? This equation 5. We also again want to solve this equation, use this equation 5 to understand the causal structure of the Schwarzschild de Sitter black hole. Okay, yeah, this one. So once again, we saw that here R equals to 0 for Schwarzschild de Sitter metric. Yes, this one. R equals to 0 is the horizon. Sorry, is the singularity. Is the singularity. And R equals to infinity is the future or plus minus future infinity or future infinity or the past infinity. Okay, so we will start again from here somewhere. You will again use this equation and try to solve this null geodesic equation. Okay, so I'm not sure if you're following the de Sitter literature these days, but there's a tons of new papers coming inspired by Witten, who show that de Sitter actually has many observers. Okay, de Sitter doesn't only have one observer sitting, and that's why it is very important to take into account what kind of observers you are talking about before you talk about the geometry. And basically, inspired by this idea, we started thinking about the observers. Yes. And we realized that the surface gravity thing, so whenever you have a geometry, I'm pretty sure more or less people will know that there are standard techniques to compute the surface gravity. Okay, and the surface gravity is very important because the surface gravity is the one which sets up the temperature of your geometry. Okay, so this is the standard equation for relating surface gravity and your Killing vector, right? Your time-like Killing vector. This is the standard equation that people use. Now, the thing is, for ARIES black holes, for example, if you take this whatever, like this boundary, the observers in the boundary are called free falling observers. Okay, why? Because they are not accelerating with respect to something. So the observers living in the boundary, in this case, like observers living in here, are free falling observers. Okay, and also in the de Sitter case, the observers living in the pole are also free falling observers. Now you see that in de Sitter case, in de Sitter black hole case, basically whatever observer you are living here, you are actually surrounded by both black hole horizon and a cosmological horizon. So what happens is that the black hole horizon tries to push you in, and the cosmological horizon tries to push you out. So two kinds of motion is actually going on here, unlike the just empty de Sitter case or ARIES black hole case. So in order to find the observers who are free falling, you have to solve the free falling equation of motion. And the free falling observers actually live at some point at some fixed radius at r equals to r naught. And how do you actually determine this r naught? Is actually solving this equation. So that means this free falling equation, free falling observer means this, okay? That means your acceleration is actually 0 in these geometries. And for de Sitter black hole case, this actually turns to an equation like this. And once you actually solve these free falling observers, this radius at this fixed radius, if you are at this fixed radius like this at r equals to r naught, only then you are not actually accelerating towards anything. You can actually be fixed there. And the point is that we will now solve the null geodesics like these equations. This equation, null geodesic equation, and we will put r naught in these fixed radiuses. Once you actually put this r naught in these fixed radiuses and try to then do the integration. So we for SDS case we start from r naught and we can go towards the singularity, right? Or we can start from r naught and go towards infinity. That means in this case, in the first case, you will reach towards the singularity of the geometry. That means the black hole singularity. Or you can actually go towards the other asymptotic region, which is the cosmological region. So you have two choices. And now you can do both of these integrals very carefully for any mass of the SDS black hole. And basically you can see that the integral actually takes this kind of form. Okay, so the expressions of TB and TC are given below. But my point is that you see for TB, the answer is purely positive, right? And for TC, the answer is purely negative. That means, yeah, this is the geometry that I wanted to show you. This is the punchline here. So basically, this is the fixed radius I was talking about, that you fix the observers there, and then you start shooting the null rays. And you see, if you want to reach the center of the singularity, you have to actually come down a bit from here to here. But if you actually want to reach the center of the future infinity, you have to go up. So this is a famous artifact of this theorem called Gao-Wald theorem, which more or less says that any positive perturbation in de Sitter actually makes the Penrose diagram taller. Okay, so before I told you that here you see that only these points are connected with each other, right, by null rays. But in the de Sitter case, you see that the causal connectivity of our geometry has actually increased. That means points even here, they can meet with each other. And causal with each other.
Counterintuitive, because if it's an accelerating space-time, you should do null rays. They should meet.
So the point is that if there is a black hole, the causal connectivity of your geometry actually increases.
Yeah. Is it counterintuitive for accelerating space-time? It's very surprising, right? I would have think because it has a horizon. I would have thought that maybe the causal connectivity would decrease.
No, actually, it increases because of this Gauss-Wall theorem, and because of the Gauss-Wall theorem, the sign of the sign is different here. You see, both are positive, but here one has negative sign and one has positive sign. So this actually means the black hole horizon and the cosmological horizon actually works in very different way. When there is a black hole horizon, this kind of integral usually ends up with something positive, and for cosmological horizons, this kind of integral usually ends up with something negative. So the perturbation, if you send perturbation towards black hole horizon and perturbation towards cosmological horizon, they act very, very differently. So this thing that I wanted to understand is because, like, at the end, we want to understand the quantum dual of these horizons. And that's why we want to understand how these horizons actually behave under perturbation. Yeah. Yeah.
What is the interpretation? Because in one of the cases, the temperature looks negative.
The temperature is not negative. You mean the sign?
It's troublesome, right?
No, it's just an imaginary number, so it can be positive or negative. For outgoing geodesics, one is minus. Yeah, this is for ingoing geodesics actually. That's why it's a minus, and this is for outgoing geodesics. That's why it's not a big deal. Yeah, because it's an I. So this is one thing I wanted to tell you, that in order to do this kind of computation, you have to do this kind of Hawking-Bousso normalization, like this. So usually this is a killing vector, right? And but the point is that if you actually have this kind of killing, if you just take this as a killing vector, then the temperature that you get in de Sitter space-time, de Sitter black hole case, at RB equals to RC, both temperature is 0. So Hawking and Bousso first showed that why you actually need this kind of free-falling observers. And when you actually take these free-falling observers into account, there is a gamma factor there, which is called Hawking-Bousso factorization, like this. This actually makes sure that the temperature is not 0 at RB equals to RC, but given by this number, which is called Nari temperature.
Beta is just 1 over temperature.
Yes, beta is just 1 over temperature. But beta becoming 0 is, temperature becoming 0 is a bit troublesome, because Hawking and Bousso showed that in the Nari limit, the de Sitter black hole is actually takes a form like this, ds2 times s2. So the temperature should be given by some de Sitter kind of temperature. Anyway, long story short is that if you actually have de Sitter black hole, me, Jan Peter, and these people found out that the Penrose diagram is actually quite different than what we knew so far. Is that the Penrose diagram for the future infinity is actually bent out. Now this is for d equals to 5, and if you carefully do this integration for d equals to the Penrose diagram than before. So here you have to go up, but not all the way up like before, like this. This one was symmetric, right? But this here the integration results were actually symmetric. That's why the causal structure is also symmetric. But in this case, for d equals to 4, the causal structure is actually not symmetric. And so this was one of the findings of our paper published in JCAP. But then I wanted to understand what are the physical quantities that we can compute, and see that because of the different causal structure, we are getting some some quantity we are computing, and we are seeing that there is some effect of this kind of weird causal structure. So basically, let's skip these things and yeah. Oh, by the way, I just wanted to mention that in the Nari limit, when you take the Nari limit, that means RB becomes RC. Only in that limit, the Penrose diagram is squared again. And another thing is that you see that when you actually take the de Sitter limit, that means RB goes to 0. You see the real part of the integration is 0. That means for empty de Sitter, as we said, the causal structure is going to be like a perfect Penrose diagram. But whenever you introduce the mass of a black hole in the de Sitter space-time, this causal structure started becoming like this. So why these are important? These are important because lately people are claiming that actually DS3 geometries are dual to some sort of double-scaled SYK model. That means from the 2-point function of the DS3, you can actually compute the SYK model. And one of my goals was to then compute the quasi-normal modes of geometry, and see that whenever there is some extra real parts always popping up, which are not 0 unless you take empty de Sitter limit or the Nari limit. And this is one of the big motivation of one of our papers just recently published. And then the other quantity that I wanted to compute is called complexity, and finish out discussion. So before we end up, do you guys know anything about shock waves? It's recently have been surfacing in the literature a lot to understand. So in the shockwave geometry, what happens is that this is the standard vacuum Einstein equation, right? And when there is a shockwave present, let's say you see here the shockwave is present along some direction, like this direction. Okay. So what this shockwave geometry actually means is something like this. Let's see. In that case, so we now have a source term for shock waves. And in the case of shock waves, this T mu nu is given by 1 over g Newton delta of u delta u mu delta u nu. So basically, shockwave means that you just put a delta, like a delta function perturbation in your geometry, and from these two pictures, you see that the black hole horizon and cosmological horizon acts very different ways. So this is like a black hole horizon. This one, sorry, I didn't write it. And this is a de Sitter horizon. Okay, so the left picture is just for black hole case, and the right picture is just for empty de Sitter case. So you see, you start from here, and once you meet the shock wave for black hole case, it actually goes up, and then you continue in this path. So this kind of thing is called time advance. Okay. So when there's a positive perturbation for black hole case, there is a time advance. And when there is a positive perturbation in the de Sitter case, you see, then actually the time actually gets delayed. So that's why black hole horizon and cosmological horizons are very different. using this property, people constructed this kind of wormhole geometry using shockwaves. How? Let me read all this again. Sorry. Yeah. So how did people make these wormhole geometries using these shockwaves? So imagine that there was no shockwaves, right? So what would happen that this guy will go this way and become and just drop in here, right? So if there is no chance a guy in here and a guy in here can meet with each other if there was no shockwave. But now, if there is a shockwave, what will happen? You go this way with a shockwave, you go this way. Sorry. You go this way and then actually come down here and then you start traveling again. So actually a guy in here now can actually meet you. So that's why in de Sitter geometry, a positive energy shockwave can create a wormhole. So this literature is also very popular these days. People are very actively working on it. So I just wanted to give you a rough idea what is a shockwave, and a shockwave geometry is nothing but you have some T mu nu, and basically that's a delta function. So this kind of shockwaves actually can create wormholes in de Sitter case, unlike the black hole case. In the black hole case, the negative energy shockwaves actually create a wormhole, and using those wormholes, people solve this kind of Hawking information paradox using ADS-CFT. In case of de Sitter, it's not completely done, but there is a work in progress because these wormhole geometries are the one which can actually give rise to solutions to Hawking information paradox. So this is one example of shockwaves, and I wanted to mention one last thing before I finish my talk, is that because of this bending, the shockwave geometry is actually much more predominant than before. Like you see that in case of de Sitter case, if there was no shockwave, if there was no bending, if there was a shockwave and there was no bending, the delta tau c is actually much more smaller. But actually, if there is a bending present, there are actually more information you can transfer to these wormholes. So how much information you can transfer to these wormholes is also one topic of discussion, which is going heavily in the literature. And I want to also finish some of my own research on this line. But combining this de Sitter geometry, de Sitter shockwaves, and stuff like this, although we don't know still the quantum dual of the de Sitter, we are going much forward in this direction to understand the quantum dual of this kind of geometry. So with this, I want to actually end this today because it's getting too long. Please ask any questions if you have any. Thanks.
I had a question.
Yeah.
What's the particular reason why around here?
So if there is like de Sitter 3, okay, in de Sitter 3 there is only one horizon actually, meaning that it doesn't have two possible real root solutions, okay. And in case of de Sitter 5, what happens is that it's a bit easier to handle analytically because in those cases, wait, just yeah, you see that this metric is basically symmetric with each other.
We can go also higher, like say 7 or.
Yeah. But those are not like physically very interesting towards me. So in case of decimal 5, that means d equals to 5. You see, this is r square and this is also r square. That's why it's a bit symmetric and easy to handle the integral.